Alright, hello everyone. This is going to be the lectures covering chapter 4.5, 4.6, and 4.7. I'm condensing everything into like 3 at a time just because it's all roughly the same material and we are trying to get through all of chapter 4. So last time we finished up with a couple of observations. The first one is that since we have the unit circle is how we choose to define sine, cosine, tangent, and all that, and because every point on this unit circle defines a right triangle, well, I mean, I'm not going to go through everything we did last time, but suffice it to say that this side winds up being the cosine of theta, if this is theta, and this side winds up being the sine of theta. So a really easy trig identity is that because we have the Pythagorean theorem, we know that cosine squared of theta plus sine squared of theta is going to be 1, because hypotenuse is 1 and because Pythagorean theorem. So that's a really easy identity, and we are going to wind up using that later. But we also noted that because sine is essentially talking about the x or the y-axis, and cosine is talking about the x-axis, that if we had sine of, I'm going to switch variables here to x instead of theta, sine of x plus pi over 2, well, since we are adding something to the x term, if we remember, like with circle centers and parabolas and moving things around, anytime you mess with the x term itself, it winds up shifting things back and forth on the x-axis. And what that amounts to here in the unit circle is a rotation, right? So if we have sine of x plus pi over 2, that's going to correspond to a rotation by pi over 2 clockwise, sort of the opposite way that we normally go, because we have to remember whenever we have plus on the x, it winds up doing, like, sending it to whatever, in this case, negative pi over 2 is. So if we look at the graph of sine, we see that it looks something like this, more or less. And if we were to do sine of x plus pi over 2, well, what that's going to do is it's going to shift this entire thing this way, so to the left, by pi over 2. And that's actually going to correspond to, well, pi over 2 is right here, and so if we were to shift the entire thing to the left by pi over 2, we would wind up taking this point and shifting it to here. We would take this point and shifting it here, and likewise everything else would shift with it. And in fact, when we look at what function that is, the function that looks exactly like sine, but with its first peak at 0, this is exactly the graph of cosine. And this makes sense because, again, looking at the unit circle, if we were to rotate everything by pi over 2 clockwise, so against the way we normally measure angles, we've effectively turned sine into cosine, right? Because we rotated it by 90 degrees. And again, 90 degrees is pi over 2. So sine of x plus pi over 2 is actually exactly the same as just cosine of x. Likewise, if we do the other thing, if we rotate by 90 degrees the other direction, we get that cosine of x minus pi over 2 equals sine of x. And again, that would be taking this graph and shifting everything by pi over 2 to the right, which of course is just going to undo what we did last time. Alright, so that's just recapping some of the last things we did last time. We also noticed that we can put a bound on these trig functions. Don't look at that. We can put a bound on these trig functions because the maximum value that they will ever go to is 1, and the smallest value that they'll ever go to is -1. They'll sort of oscillate back and forth between these two values, but they'll never get beyond them. And this is a product of, we know right around the origin it's bounded, and we know it's periodic, which means that when you shift it by some amount, it looks the same. So if it's bounded right here, and you can shift it and it looks the same, it has to be bounded everywhere. However, if we wanted to have a version of a sine curve or a cosine curve where the bounds were different, like let's say we wanted to have where it goes all the way up to 3 and all the way down to -3, we can achieve that relatively simply. The first thing that we have to notice is that sine curves and cosine curves are effectively no different than any other function. Like if we think back to chapter 2 or chapter 3, one of the ways we can augment functions is like if we have f of x, well then we can have some constant times f of x, and that's going to stretch things, right? Unless it happens to be less than 1, in which case it's going to compress things vertically. So if we wanted to do the same thing but with sine and cosine, there's no problem, we can just do that. So if we wanted a sine curve that goes up to 3 and down to -3, it simply is going to be 3 times the sine of x. And we can check this. I think I gave you a plot of this exact function, but of course it's going to look roughly like sine, but it's going to look a bit more compressed because when we zoom out, we see that we're seeing more coverage in the y direction and less coverage in the x direction, because to zoom out to where this is at 3 and this is at -3, our viewing window has changed. Like, again, thinking all the way back to probably chapter 1, when we change our viewing window, everything kind of gets smushed around. And so even though we do still have a period of 2 pi, even though we still have the zeros are all in exactly the same places, because we've changed the height, the sort of bounds of this function, when we zoom out, it's going to change the way it looks. And so with this, we can also plot what happens if we have like 1/2 sine of x, and this is going to do probably exactly what you would expect it to do. It's going to shrink everything vertically by half. So it's going to look something like this, where everything is half as tall as it used to be. The peaks are half as tall and the troughs are half as deep. And so this actually gives us our first sort of fundamental augmentation of trig functions, which is called the amplitude. So the amplitude, the amplitude is going to be half the bounds. And so when I say bounds, I mean that if I give you a curve and it goes something like this, and it goes from -4 to +4, well, the bounds would be 8, right? It's between a total of 8 units. Essentially, you can find every point on this function within a range of 8. So, to figure out what the amplitude is, we would simply divide 8 by 2, which is 4. Another way to think about this is, since the bounds are usually symmetric, right, it goes up to a and down to -a, then the amplitude is just going to be a. However, we are not always going to have it where it is symmetric like that. Sometimes we're going to have the bounds go from like 10 to 3. And then figuring out the amplitude would be something else, right? So let's actually do that as a really quick example that I don't have in the notes. If we had a function that looks like this, you know, this isn't a sine function, it's not a cosine function, it's something, but let's just say it's bounded between, here is going to be 10, and here is going to be 3. And then I ask, what is the amplitude of this curve? And using the definition that it's half of the bounds, then we find the distance between the bounds, which is going to be 10 minus 3, or 7, and then the amplitude is just going to be half that. Essentially, all we are finding is where's the middle of the curve, and the amplitude is just going to be the distance above middle or below middle that it goes to. And finding the middle is as simple as taking the upper bound and the lower bound, subtracting one from the other, and cutting it in half. So, yeah, there are other fundamental ways we can mess with or augment sine and cosine curves. And in fact, we actually just did that a little while earlier when I was talking about adding or subtracting pi over 2. What that amounts to is called a phase change. So the phase is loosely the shift right or left of the function. Classically, it's actually defined in terms of the unit circle, where we say the phase is going to be, well, right now, having cosine aligned with the x-axis and sine aligned with the y-axis, we have a phase of 0. That's sort of standard mint condition unit circle. But if we were to take this and rotate it by some amount, that corresponds to, when we plot it against the angle, that corresponds to taking the whole thing and shifting it either forwards or backwards, like we just saw at the beginning when it came to adding or subtracting pi over 2. We can rotate everything by 90 degrees this way, in which case cosine now looks like sine, or we can rotate everything 90 degrees this way, in which case sine looks like cosine. Both of those are examples of a phase shift. And so if the amplitude looks like having something times your function, then a phase shift is achieved by doing exactly what we were doing before. We add or subtract something. I don't know where. Oh, I see. Yeah, so I'm not going to do that right now just because it's a little hairy. But yeah, so we have these two different things we can look at. And effectively what the phase does is shift things forward and back, but not up or down, right? Just like when we have y equals x plus 2 squared. Well, this is going to look an awful lot like y equals x squared, right? Like a standard parabola. But because we have this plus 2 in here touching just the x term, it's going to shift things right or left. And in this case, because we have plus 2, it's going to shift things over minus 2. So the new graph should look like this, where this is 2 and that was 0. So phase is a really simple one. It's sort of an exact analog to the way we have been augmenting functions. This next one, which I was looking at by mistake and why I got confused there, is called the period. So last time we defined and looked at what the period is. It's sort of how often something repeats itself. And when it comes to standard sine or cosine, because they repeat exactly once when they go around the circle is 2 pi radians, so the period of each of these functions is going to be 2 pi. And when you look at the graph of sine and cosine, the distance between successive peaks or successive troughs is going to be exactly 2 pi. However, there are ways we can manipulate this. The first way, well, the first step is we are going to have some alpha that we multiply by x. So when it came to the phase, we were adding something to x. Now we are going to be multiplying something onto x. And what that is going to do is it's going to change where sine thinks the different values are. If we were to have alpha equals 2, it would effectively think every x value is 2 times farther away than it is, and so we would expect to see the period actually shrink by half. And that's just because it's going to think 10 is at 5, right? So between 1 and 5, it's going to actually plot all of between 1 and 10 because it thinks 5 is 10. If that's a little hard to think about, just go find a graphing calculator and try messing around with it. You'll find that the bigger the number this is, the more compressed the period is, right? So these have an inverse relationship. And in fact, when we go to figure out exactly how to change this, like if I want to change the period to an exact number, the first step is to change it to be exactly 1. And the way to do that is to, like I was saying, if we had like 2, if alpha was 2, then it would think 10 is at 5. So it'll take the whole distance between 0 and 10 and squish it to be between 0 and 5. So if we want a period of 1, we should take the regular period and smush it all to be between 0 and 1. The regular period is 2 pi. So if I multiply right here by 2 pi, then at 0, this is going to think it's 0. And at 1, this is going to think it's at 2 pi. So it turns out that when we have the sine of 2 pi times x, it's going to compress the sine curve, or just as easily the cosine curve, to be between 0 and 1 instead of between 0 and 2 pi. What this does is now we can use this because this has period 1, we can use that as like a standard candle to start figuring out how to do other periods. It would be fairly difficult if you just had sine of x to figure out a number to multiply by so that you got a period of exactly 6. That would be kind of hard. However, it becomes super easy when we first compress it to 1, and now to take it to 6 is going to be the same as dividing by, in that case, 6, so that it stretches everything out to 6. So the technique used here is to first normalize the curve to be having a period of 1. Then, once you have a really nice behaving period, you can augment that much easier and take it anywhere you want. So I put a B here simply because amplitude usually takes an A and the period usually takes a B. So when we have B equals 2, let's say, in effect what we have is the sine of 2 pi over 2 times x. And the 2 pi times x is going to take regular sine and compress it to be between 0 and 1. And divided by 2 is then going to take that between 0 and 1 and stretch it to between 0 and 2. So that is going to exactly produce a sine curve with a period of 2. And it's achieved by first compressing it to have a period of 1 and then stretching it to have a period of whatever else you want. So looking at, so just some of the examples that we did in there is if we wanted to have a period of exactly 5, then it's pretty easy. In this formula, we just substitute b equals 5. And so we would get the sine of 2 pi over 5 times x. And I believe on the next page I actually have that plotted. Oh, I used cosine. Alright, that's fine. When it's cosine, it's exactly the same formula. You obviously just switch sine for cosine. And when we do this, we should get a function which has its first peak at 0, like cosine always does, and then the next time it reaches a peak, right here, is going to be at 5. And of course, the peak going this way should be at -5, and it should repeat perfectly forward and backwards forever. But what we've done is by multiplying x by 2 pi over 5, we have essentially stretched and compressed it in exactly the right way so that the period goes from 2 pi to exactly 5. Right, so with those three, we have nearly everything. All the normal ways to mess with and augment a sine or cosine curve. So we have amplitude, phase, period, distance between successive peaks or troughs. So like on the sine curve, you'd say this is a peak, this is a trough. It's very tempting to try to define the period by the distance between the zeros, but because this thing goes up and down twice for every peak, you're actually going to have twice as many zeros as you do peaks. So it's very tempting, but we should only measure the period by the distance between successive peaks, right? So this distance is the period. Likewise, this distance is the period, but not that. That's actually going to wind up being exactly half the period because of what I just said, that there are 2 zeros for every one peak, just because it goes up and down once for a single peak, and that's going to mean it crosses the x-axis twice. So we have amplitude, we have phase, we have period. How do we put all of these together, right? So if we use A for amplitude, actually flip these, so I'm going to have B for period, C for phase, and then there is one more, but it's kind of boring. It's the height, right? So this, I'm not even going to define it, it's exactly what you'd expect. Like, just as we can have y equals x squared plus 3, and this looks exactly the same as just a parabola, but shifted up by 3, that's all that this last parameter does. So, if we put all of these together with their appropriate variables, we can have a general formula for, I'll just say, a sine curve, even though it is technically for both sine and cosine. This is going to be a sine of 2 pi x over b, the period, plus c, the phase, and then all plus d, and that just sort of shifts it up or down. These are the 4 parameters that all trig functions share, at least the main 3. When we get to secant, cosecant, and cotangent, their graphs don't necessarily look the same, so we'll have to think about those differently. But for sine, cosine, and mainly for tangent, these are the 4 ways we can mess with it. And they do have analogous things in regular functions like polynomials, right? If I add 1 to x every time it shows up, that effectively shifts it to the left by 1. If I add 1 to the entire thing, it shifts it up by 1. Unfortunately, we don't really have the same concept of phase when it comes to polynomials, but we do have amplitude, and that's, again, you just multiply everything by some number and it stretches or compresses it. So this is going to be our general formula for a sine curve, or for a cosine curve, just with the right function. So doing this, I'm going to give myself a little room. Doing this, let's see if we can sketch f of x equals 5 cosine of x plus pi over 2. So we should run down the list, right? So what is A? What is the amplitude? The amplitude is going to be whatever number happens to be right here, which of course is 5, right? So given this, we know what the bounds are. Given the bounds, and if there were any d term here, the shifting, we would know exactly what the bounds are, right? So we know what the distance to min and max is going to be 2 times 5. And if we had the whole thing shifted up or down by some, we'd know exactly where on our graph it goes. In this case, since it's just, adding 0, there is no shift up or down. But this means, now I know that the curve is going to be, f of x is going to be between -5 and 5, which is hugely valuable for us to sketch it, because now we know we don't have to look anywhere else, and if we do wind up going anywhere else, then we've made a mistake. So next question, what is our period? So since this is just plain old x, I'm not sure you can see that, but take my word for it, this is just plain old x, then we must have 2 pi over bx equals just x. There's only really one way to do this, and that's going to be, so we can divide both sides by x, we get 2 pi over b equals 1, and then we multiply both sides by b to get 2 pi equals b. And so we get that the period is exactly 2 pi, which also makes sense because we know that the cosine of just x has a default period of 2 pi. So this is sort of another way to confirm that. So we get that b must be 2 pi. So now we know how long it takes for the function to repeat itself. If we look at c, we get c is equal to positive pi over 2. And so if we remember the addition reversal thing, if we add something to our x value, it shifts it the opposite direction. So by adding positive pi over 2, it's actually going to shift everything towards negative pi over 2. And so our last one is d, and d happens to be 0 here because we're not adding anything to the function. It's not shifted up or down. Using all of this information, I can then give myself a little plot, and I know, all right, cosine of 0. Cosine of 0 is going to be 1, but we don't have cosine of 0. We have cosine of 0 plus pi over 2. Cosine of pi over 2 is going to be whatever the x value at this point is, which happens to be 0. So the cosine of pi over 2 is 0, and then 5 times 0 is 0. So at x equals 0, our output is going to be 0. I can also immediately start drawing other points because I know that over here at 2 pi, everything repeats. So if it's 0 at 0, it had better well be 0 at 2 pi as well. And same over here for negative 2 pi. In fact, I can put 2 more points because I know that the zeros are half the period. So right here at pi, it should be 0, and right here, negative pi, and here at positive pi, it should also be 0. Now, we know that this thing goes from negative 5 all the way up to positive 5, so let's find the first case where we have 5, right? So we're going to have 5 when cosine of all of this is 1, right? Because then we just have 5 times 1. So when is cosine of x plus pi over 2 going to equal 1? Let me give myself a little bit more room over here. So cos of x plus pi over 2 equals 1. Well, I know when cosine equals 1, cosine equals 1 at exactly 0 and 2 pi. So I want x plus pi over 2 to be 0 or 2 pi. Well, if we just do the easier case, then we have x plus pi over 2 equals 0, and we get that x has to be negative pi over 2. So now we can come over here. If this is pi, then this is going to be negative pi over 2, and we know that is going to be the first instance on our graph where we have 5. So right here, we're going to have a point which is, I didn't draw that to scale, but yeah, so right here it's going to be 5. And so now I know where the first peak is. I also know the general shape of a cosine curve, so I can start connecting things. I go through the 0, down here I have to reach negative 5, and then come back up to reach the next 0, and then go up to 5 again. And I get something that looks incredibly crude, but that is a sketch of 5 cosine of x plus pi over 2. And if you look at the graph that I've included in the notes, then it should look, much more professionally, but should look something like this. If we do the next one in the notes, if we sketch the next one, which is negative 5 sine of x. Well, this one's even simpler, right? We can go down the list, but in fact, the only one that we've changed is the amplitude. So we have everything is going to be stretched by 5, but because it's negative 5, it's also going to invert things. Just like when you have negative x squared, this gives you an upside down parabola rather than a right way up parabola, and that's just because of the negative sign. So to sketch this, this is going to look exactly like sine stretched vertically by 5 and flipped upside down. So what does that look like? I know Sine has a 0 at 0, and it normally goes up from there, so I know it's going to go down. And then the question is how far? Well, by the amplitude. It's going to be bound between, it's still going to be bound between 5 and negative 5. So I know it's going to go down, 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 down until it reaches 5, and then it's going to come up, 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 and so on. It's going to look like that, again, roughly. And I picked these two examples on purpose because this is actually the exact same sketch that we had for the previous problem. Right? For the previous one, we had f of x, can you see that? I think so. We had f of x equals 5 cos of x plus pi over 2, and it turns out it yields the exact same curve as negative 5 sine of x. This makes sense because what we were saying before, we know that cosine of x plus pi over 2 looks, well, last time it was minus pi over 2, and that made cosine turn into sine. So because we have plus pi over 2, that looks like taking our cosine, which is the x-axis, and rotating it down even further. And down here, the value, the x value that you get from looking at this as your new function is going to be exactly the same, but opposite from normal sine. And so we get the interesting other identity that cosine of x plus pi over 2 equals negative sine x. And that's because positive sine x goes on the positive y-axis, and if you take cosine and rotate it clockwise by pi over 2, it looks exactly like sine, but in the negative y-axis. And so we get that, well, we get that. There's a comparable one for sine. Minus pi over 2 is the same as negative cosine, but since it's not super useful, we're just going to leave that in the notes. Okay, so this gives us another type of problem that we can encounter, which is, here's a function with respect to cosine. Can we rewrite it with respect to sine? So that's exactly what this example says, is rewrite f of x equals 3 cosine of x over 4 plus 9 pi over 2 plus 2 with sine instead. So we're given a function with cosine in it, and we know we have this phase relationship between sine and cosine, so can we rewrite this to use sine instead? And the answer is, of course, yes. I wouldn't include it as a problem unless there were a way to do it. Bear with me, I'm just finding. Yeah, so let's go down the line. So we have A is equal to 3, B is equal to, well, if we have 2 pi over bx equals x over 4, again, we can cancel the x's, and then I'm going to multiply everything by b to get 2 pi equals b over 4, and then multiply everything by 4 to get 8 pi equals b. So we know that b is going to be 8 pi. And what that tells us is that this function has a period of 8 pi rather than 6 pi. All right? C, which is the change in phase, is going to be this, 9 pi over 2, and because we're looking to convert from cosine to sine, this is actually the parameter that we want to look at the most. Everything else doesn't change when we switch from sine to cosine. Like the amplitude, the period, and the shift up or down doesn't change whether or not it's talking about sine or cosine, because the sine-cosine relationship is purely based on the phase that we need to look at. And then we also have d is equal to 2. So to rewrite this in terms of sine, we need to figure out what 9 pi over 2 looks like for a sine function. And so first, let's just look at 9 pi over 2. So 9 pi over 2, if we think about it, 8 pi over 2, no, so 4 pi over 2 is exactly 2 pi, right? So since we have 9 pi over 2, we have significantly more than 2 pi. But we know that on the unit circle, if you go past 360 degrees and keep going, well, it's just the same as just going that little bit, right? Like, what did we find? We found that 420 degrees was the same as, what was it, pi over 6, I think? Something like that, where you go all the way around and then just a little bit further. And because 2 pi is the period of this function, we know that shifting things by 9 pi over 2 is going to be the same as shifting by whatever is left over when we subtract off 2 pi. So that's exactly what we're going to do. We're going to subtract off 2 pi to figure out where this thing lands on the normal unit circle. 2 pi has to be written with a denominator of 2 though, so it has to be 4 pi over 2 so that the denominators match. This gives us, well, 9 minus 4 is 5 pi over 2, which is still too much, so we're going to do it one more time. We get 5 pi over 2 minus 4 pi over 2 is just pi over 2. So you find that even though we have a phase shift of 9 pi over 2, when we figure out what the remainder is, basically by dividing by 2 pi, it's pi over 2. So, since everything else is going to be equivalent under that remainder, I'm just going to rewrite C as pi over 2. Now, we know all kinds of stuff about sine and cosine and phase shifting by pi over 2. So, we can see what happens. If we have cos of x plus pi over 2, we know what that is. We in fact just did a whole question where we found out that this is equal to negative sine of x. And this is where we're going to get this conversion, right? The question asks us to rewrite this cosine function in terms of sine, and we found that the phase of this function actually gives us that conversion. So that's very nice. If it didn't give it to us exactly, we would have to perform the phase shift to get to sine, and then figure out the phase shift we'd have to do to get to whatever it was at. But since this one's very nice, we get the conversion sort of nice and cleanly. So we know this is true, and the question is this the same as having x over 4? And I say it in the notes, but yes, it is the same because all of these parameters are different. They all adjust fundamentally different properties of sine and cosine. So if we were to change the period, but not the phase, we would stretch or shrink it, and then if we change the phase, it would shift it right or left. That's going to give us the exact same answer though as if we have the regular thing, we shift it right or left, and then compress or stretch it. So it doesn't really matter which one we do, and each one is just going to tell us one fact about it. And these facts are all co-compatible. So we know that having cosine of something plus pi over 2 is the same as negative sine of that something. This means, since the phase is the only thing that's affected by our transition from cosine to sine, we can rewrite this. We know that this 9 pi over 2 is going to go away, and it's going to be replaced by having this all be negative sine. So now we have 3 times negative sine of pi over 4 plus 2, because all of the other parameters don't change. This negative sine I'm just going to bring out to the front so that we get negative 3 times sine of x over 4 plus 2. And if we go and super double check everything and we plot both this and this at the same time, they do perfectly coincide. So that gives us a nice little reassurance that what we're doing is correct and valid. Okay, so this question is going to use everything that we've seen so far to figure out how to create a single cosine or sine function that satisfies a list of requirements. So this one says, find f of x so that All right, the maximum, so we're going to have f of x is going to be bound between 2 and 5, which is what the first thing says. It has a maximum of 5, and a minimum of 3. That 2 says that it has its maximum at 2. So this tells us f of 2 equals 5, our maximum. And the distance between inflection points is 3 pi. So I'm not going to go into the same amount of detail I do in the notes, but basically an inflection point is where a curve goes from being curving up to curving down. So right here would be an inflection point. Since sine and cosine, basically all they do is change from one to the other, then we see that for a regular, let's say cosine curve, every one of these points is going to be an inflection point. But they happen to exactly coincide with the zeros of this function. And we know something about the distance between zeros. So, saying that we have the distance between inflection points as 3 pi instead of the distance between zeros probably tells us that the zeros are not at the same place as the inflection points. And we'll see why that is later on. But so we have these facts, and now we have to go about building a function that does all of this correctly. Alright, so the first one's going to be easy. What's the amplitude, right? So the amplitude is always half of the bounds, right? That's how I defined it earlier. Since our bounds are from 5 to 3, we know that... Wait a second. So I'm just noticing that in the notes I did that wrong because I made the same mistake when I typed up the notes that I did just now by confusing the lower bound with 2 instead of 3. So what I have in here is incorrect. So if you watch this and then you go call me out on Campus Wire, we're all good. I already know. But that's fine. We can keep going. So the difference between the bounds is just going to be 5 minus 3, which is 2, and then half of that gives us the amplitude. So we know that the amplitude is 1. That's super handy. The next thing that we can figure out is going to be what d has to be. So if we remember, d is by how much it's shifted up or down. And we know that we're going to have some amount that it's shifted up simply because 3 and 5 are not symmetric about the y-axis. So we know we're going to have to shift by some amount. And it turns out that the amount that we're going to have to shift by is, if we have an amplitude of 1, that means that the maximum of an unshifted curve is going to be at 1. So by how much do we have to raise it up so that the maximum is at 5 instead of at 1? And of course that answer is going to be 4, right? We have to shift everything up by 4. And I'll just redraw that really quick. If we do have this, it's going to shift everything up by 4, and in fact we're going to have the highest part be at 5 and the lowest part indeed be at 3, because the total difference in height from max to min has to be 2, which is why we picked an amplitude of 1. So it goes up by 1 and down by 1 for a total y change of 2. So it goes from 5 to 3 and back again. So this tells us that d has to be 4. Another way to think about this is whatever the maximum is has to be exactly 1 amplitude above the center line. Right? So that makes sense geometrically, but what does that translate to formulaically? Well, this tells us, these two facts basically say d has to equal max minus amplitude. So we take the maximum value this thing has to go to, And if we know the amplitude, then we know how far below the amplitude the center line is. And the center line is going to be the value that we have to shift up or down. So, in this case, it happens to work out perfectly. The maximum is 5, the amplitude is 1, and 4 is indeed 5 minus 1. So, that is maybe a quicker way to do things, but it uses exactly the same intuition. Next, we have to figure out the period and the phase, right? So, we know if we had a function that wasn't shifted up or down, then the inflection points coincide exactly with the inflection, with the zeros. I was going to say the same thing twice. The inflection points coincide with the zeros. We also know that the function goes up and down per peak, which means that it crosses the x-axis twice for every one peak. So, the distance between peaks is going to wind up being exactly 2 times the distance between zeros. Since we don't have any zeros because everything's shifted, it's going to be the distance between the inflection points. So, to figure out what the period is, we need to figure out 2 times the distance between the zeros, and we're given that the distance between the inflection points, which is the same as the zeros, is 3 pi. So we know that b has to be 2 times 3 pi, or just 6 pi. We only have one parameter left, but now we have to be kind of careful. So if we put all of this together, we have 2 choices. We could either build this function using sine or using cosine. If we choose sine, then we have 1 times sine of, we have 2 pi x over b, which is 6 pi, plus c plus 4, right? Where c is the only parameter that we have left. We can see that 2 pi over 6 pi simplifies quite a bit to just pi over 3, x over 3. And so the last thing we need to figure out is, what does c have to be? And I'm saying that we have to be careful because we can figure out c super easily if we had the regular period of sine or cosine. Since we don't, since we've already changed the period, now we have to figure out exactly by how much we have to shift things around by to get the correct values. In other words, if we were to take the unit circle and sort of squish it into an egg or an ellipse, that's effectively changing the period of sine or cosine. And so to say that sine of x plus pi over 2 is related to cosine isn't true anymore. Now it has to be whatever pi over 2, whatever that corresponds to with the new period is. So we need to figure that out. One way would be to say, well, pi over 2 is exactly 1/4 of the period, 2 pi. So we could probably employ that exact same thing here. But I'm going to show you the way to do it in general. So we start off like this, and I'll do the same thing for cosine afterwards, just in case you wanted to do cosine. But we start off with this, and then we're going to factor something out. All right, so we're going to say this is the same as sine of 1/3 all times x plus 3c. Right? If I were to factor a 1/3 out of x over 3, I just get x. And if I were to factor a 1/3 out of c, it would have to become 3c. So that when I redistribute this back in, I get c back. But now, sine of something times all of this, well, now we've effectively applied the period to the phase shifting as well. So now all we have to do is figure out what 3c has to be. And that one is going to be much easier. So let me just see where it is in my notes. Right, so we want our maximum to be at 2, right? And so we know that sine has its first maximum at pi over 2, right? Following the sine value, then as we wind around the circle, sine of 0 degrees is 0, sine increasing, and it reaches 1 at pi over 2, and then it starts decreasing again because the y value is shrinking. So we know that it has its first maximum at pi over 2. So we know that, well, hang on. We know that at x equals 2, f of x equals 5, and so we need x, no, what do we need? We need 2 plus 3c to equal pi over 2, right? So that when we input 2 into this, we need to figure out what we have to shift it by so that it effectively thinks all of this is pi over 2. And this is going to be a super simple thing to figure out. All we have to do is subtract 2 from both sides to get 3c is equal to pi over 2, and I'm just going to combine this to be pi minus 4 all over 2, and then we divide by 3. So c has to be pi minus 4 all over 6. And that's basically it. We now have all 4 parameters, and so we can now put them all together to finish out our function. And again, this is not going to match what I have in the notes because I made a mistake in the notes that I caught here, but didn't while I was typing. So these should look slightly differently. But we can put all of these together, and the beauty of this approach to sine and cosine functions is I don't need to worry about how these things intermix. All I need to do is figure out each of these individually and then plug them all into the formula. So we get sine of b is 6 pi, but when we do 2 pi divided by 6 pi, it just winds up being x over 3, and then c plus pi minus 4 over 6, and then the last thing we have is d, which is plus 4. Yeah, that's a lot. But now, when we go to check things, again, the thing I have in the notes is just dead wrong, so I apologize for that. But if we were to graph this, we would see that it has all of the things that we want. At 2, it's going to be 5. It's going to have a long period because it has period 6 pi, which is 3 times longer than normal. And it's going to have a minimum at, dang it, I almost did it again. It's going to have a minimum at 3. So, yeah, the period is going to be 6 pi, the amplitude is going to be 1, it's going to be bounded perfectly between 5 and 3, and it has its maximum at 2. So, we did it. We checked off all the little boxes, and that question is done. So that's the end of 4.5, but we're going to just roll straight into 4.6, and this talks about more functions. So far we've only used tangent once, and that was when we were solving that cliff thing where all we knew were the leg lengths of the triangle and we didn't know the hypotenuse. That is pretty much exactly when tangent is supposed to be used. But if we remember, we have tangent of theta is equal to opposite over hypotenuse. Oh, I'm sorry, no, that's sine. This is opposite over adjacent, so katoa. So this is referring to this triangle, right? All of these things refer to the right triangle produced in the unit circle. So if we look at what is the opposite side for this angle theta, well, it's exactly sine of theta. And if we look at the adjacent side to theta, it's cosine. So this is also the same as sine of theta over cosine of theta. And this is again why we see that we really only focus on sine and cosine, because with them we can define the third one, which is tangent. And then with those 3, we can define all of their reciprocals, secant, cosecant, and cotangent. Alright, but what are the properties of tangent? Like, what would its graph look like? Well, we have a function in the denominator. We should, by now, at this point in the semester, be alert to the fact that this might give us asymptotes, a vertical asymptote, right? Wherever cosine of theta equals 0, we're going to be dividing by 0, and we know we can't do that. So where does that happen? Well, cos of theta equals 0 at theta equals pi over 2 pi 3 pi over 2, and depending on how you think about it, either, yeah, just those. And of course, wrapping around infinitely. But so that means that tangent is going to have a vertical asymptote at each of these values. And of course, since it's a periodic function, at the next one would be, what would it be? So it would be 2 pi plus pi over 2, so that's 4 pi, so 6 pi, oh no, that can't be right. It's got to be 5 pi over 2, which is once more around the circle up to regular pi over 2. And of course going negative and positive infinite. So if that's the case, what does the graph of tangent look like? Well, what happens as tangent approaches pi over 2, the first one that we have an issue? As, I'll write this, as theta goes towards pi over 2, we see that sine of pi over 2 is 1, so it's positive, and cosine of pi over 2 is 0, so obviously it gives us an issue. But as we get close to it, sine is still positive, and cosine goes to 0. So what this tells me is tangent of theta goes to infinity, right? Because it's positive, and we're dividing by 0, so the values are going to get bigger and bigger and bigger. We just have to check which one it's going to, either positive or negative infinity. But since sine of theta is positive at pi over 2, it goes to positive infinity. And of course, from this we can extrapolate the exact opposite happens as it goes to negative pi over 2. What this tells us is that if this is pi over 2 and this is negative pi over 2, it has to be going vertically here and vertically here, and in between them, it's going to look kind of smooth, whatever that means. What happens at theta equals 0, right? So what happens at this input? Well, if we plug it in, we get sine of 0, which is 0, and cosine of 0, which is 1. So in total, we get 0 over 1, which is 0. So we know that at theta equals 0, tangent of theta also equals 0. And this gives us enough to roughly figure out what that has to look like. Since it's a periodic function, we know it's also going to repeat this infinitely forward and backwards. But something of an interesting difference is, what is the period of tangent? Yeah, so I'm going to do a little derivation right here that I also do in the notes. It's super quick though. So we already know that adding or subtracting pi over 2 from sine or cosine is going to turn it into the other one, and it might be positive or negative, right? So like sine of x minus pi over 2, this is equal to negative cosine of x. Did I get that right? No, I did not, because I forgot. Yeah, so sine of x minus pi over 2 is cosine of x. And cosine of x minus pi over 2, this one is going to be taking cosine and doing minus pi over 2, so it's going to rotate it by that. No, yeah, it should be. Oh, I see what I did, yeah, never mind. It's not pi over 2. That was a stepping stone argument that I had. But so sine of x minus pi is going to be negative sine of x. This makes sense because when we're looking at this, pi corresponds to a rotation of 180 degrees, which just means sort of flipping all the way around. So sine of x plus pi is going to be down here, which is the negative y-axis, which means it's going to be behaving like negative sine of x. Likewise, cosine of x minus pi is going to act like negative cosine of x. So, what is tangent of x minus pi? Well, based on the definition we have up here, cosine of something is equal to sine of that something divided by cosine of that something. So this is going to be sine of x minus pi all over cosine of x minus pi. And this is going to give us, well, this is, just make sure I'm getting it right. Yeah, so this is going to equal negative sine of x, because of this, and cos of x minus pi is just going to be negative cosine of x, but the negative divided by negative, they're going to cancel, and so this is just sine over cosine, but that is, again, the definition of tangent. So this is just tangent of x. All this put together means that we have tangent of x minus pi equals tangent of x. And if we recall all the way back from the first set of notes that I did when I defined what the period is, it is whatever number makes that true, right? So the definition of the period was such that f of x plus t equals f of x. And here we have tangent of x minus pi equals tangent of x. And so it fits exactly the same form, and so we see that the period has to be negative pi. Well, okay, so negative pi technically is correct, but we wouldn't say that the period is negative, because that's like saying a distance is negative. Instead, we can notice that rather than subtracting pi from everything, we could have just added pi. That's also going to rotate us around the unit circle by exactly 180 degrees, so we can just fix that a little bit, and now we get that the period for tangent is pi. This is different. The period for sine and cosine were both 2 pi, but the period for tangent is only pi, so that's one of the differences that we get with this function. Yeah, so despite these, well, this sort of only a couple of differences being tangent is still periodic, tangent still has a period, I mean obviously, tangent still also has a phase, right? You can shift it right or left on the axis. We don't say that it has an amplitude simply because it races up to infinity and down to negative infinity, but we would still say that we are stretching it. And then of course you can still go up and down. So the general formula for tangent is still a times tangent of 2 pi x over b, the period, plus c, the phase, plus d, the vertical shift. This is still the general formula for all tangent functions, and basically because you can define any tangent function as a ratio of sine function and cosine functions. So they're all going to wind up being the same thing. Skip forward on my notes. All right, so let's do a little example just to illustrate why we teach everything in terms of sine and cosine first before doing tangent. So what is the tangent of, what should I do, pi over 3? So the tangent of pi over 3 by definition is going to be the sine of pi over 3 divided by the cosine of pi over 3. But we know what both of those values are, right? We know based on our equilateral triangle derivation that the sine, I'll write it down here, the sine of pi over 3 is going to be root 3 over 2, and the cosine of pi over 3 is 1/2. So since we are dividing by a fraction, it's the same as multiplying by its reciprocal, so this is going to be the same as root 3 over 2 times 2 over 1. The 2's cancel, and we get that the tangent of pi over 3 is exactly root 3. So trying to find that through some other means, or trying to construct a triangle, or trying to say, all right, what does the tangent actually represent here? If you're curious, the tangent in the unit circle actually corresponds to a line which is tangent to the point that's forming the angle. That's why it's called the tangent. And it turns out that this distance is tangent of theta. So if we were to have this at exactly pi over 3, then the ratio of this to this would be the tangent, which would be exactly the square root of 3. That's a lot clumsier, it's a lot less intuitive, so we don't really use that part of the diagram very often, but there is still a geometric interpretation of tangent. Okay, so with that out of the way, we're going to talk about the rest of the trig functions. And we started off by naming all 6 of them, so let's just do that again. So we have sine of x, we have cosine of x, we have tangent of x, and then we have all of their reciprocals. So the reciprocal is just going to be 1 over sine of x, and we call this one cosecant. So cosecant. CSC is the abbreviation for cosecant that you'll find on a calculator, that you'll find in notes and textbooks all over the place. The next one is 1 over cosine, which is called secant, which is abbreviated as SEC. And then the reciprocal of tangent is 1 over tan x, and this is called cotangent of x, abbreviated COT. And the reason why we have 6 functions instead of just 3 and their reciprocals is that when we talk about functions, this is more of a general point, but when you have this notation, you have f of x, which refers to a function, and then you see it raised to the negative first power. The nomenclature of this and the convention is this means the inverse function, not 1 over f of x. So when you see f to the negative first, I understand that like 3 to the negative first is 1 over 3, but that's because it's a number, not a function. The convention is to say function raised to the negative first is the inverse function, not the reciprocal. So rather than constantly fighting with the notation when I want to refer to the reciprocal, mathematicians just came up with 3 new words for the reciprocals so that we can maintain that sine to the negative first or cosine to the negative first represent their inverse functions, which is what we'll tackle on the next set of notes. But yeah, so with these, we also get that since sine is opposite over hypotenuse, then cosecant has to be hypotenuse over opposite, since it's just 1 over sine. Likewise, secant being 1 over cosine should be the same as the hypotenuse over adjacent, right? Exactly 1 over cosine, which is adjacent over hypotenuse. And then tangent being opposite over adjacent, cotangent should be adjacent over opposite. And I'm saying should, but this is actually exactly how they're defined. Yeah. So, hang on, skipped something. Yeah, okay. So, when we introduce these new functions, we also get a slew of new identities. And I'm going to share with you the method that I have personally used ever since high school. Do not bother memorizing all the identities. Instead, I memorize one identity and just sort of rederive the others as I need them. So the one identity I would suggest that you memorize is sine squared of x plus cosine squared of x equals 1, the one that we started with. And this one again comes from the Pythagorean theorem and the sides of the triangle and the unit circle. Now, if I go and divide everything by sine squared when I divide everything by sine squared, this is going to reduce things, right? So sine squared divided by sine squared is 1. Cosine squared over sine squared, well, that's going to be the same as cosine over sine times cosine over sine. But we know that sine over cosine is tangent, so cosine over sine is cotangent. Since everything's squared, this is cotangent squared. And then 1 over sine is the definition of cosecant, so this is just 1 over sine times 1 over sine, so it is cosecant squared. And so from this one identity, simply dividing through by sine squared gives us this identity, which relates 1 cotangent and secant, cosecant. So this is also useful. Another thing we could have done is instead of divide by sine squared, we divide by cosine squared. And this in fact gives us the other one. So cosine x. And so obviously, sine over cosine is tangent. So we have sine times sine over cosine times cosine, so that's the same as tangent times tangent. So this is going to be tangent squared of x. Cosine squared divided by cosine squared is 1, and then 1 divided by cosine is secant, so 1 divided by cosine squared is going to be secant squared. And these three identities, I'll erase the division, these three identities are probably going to be the most useful ones when it comes to things like finding derivatives or integrals when you move on to Calc 1 or 2 and even beyond. I still use it occasionally. But there are many, many, many other identities that we have to get through. Oh, actually only like 3 pages. Okay, we can do this. So these are the Pythagorean identities with their reciprocals and all that built in. Another set is the angle sum formulas. So if we have sine of alpha plus beta, where alpha and beta are 2 different angles, well, is there a way to relate this to just sine and cosine of alpha or beta? And yes, there is. There's a nice geometric thing for it. I don't remember it off the top of my head, but if you're really interested, you can go look it up. The long and short of it is that the sine of alpha plus beta is going to be sine alpha times cosine beta plus sine beta times cosine alpha. So that is something that you will just have to straight up memorize, but it's not too hard. I do it by saying this is S, so S starts for switch, and so we have sine alpha cos beta, and then we switch them and we get sine beta cos alpha. So that's the switch, and it comes from sine. If we have cosine of alpha plus beta, it does not behave the same way. It has its own formula, and what this turns into is it's going to be cosine alpha cosine beta minus sine alpha sine beta. So I mean, I do have one for this. It starts with a C, and so I say that means combine, right? So S for sine also stands for switch, because you have the same thing twice, but with the swapped angles. And then for cosine, it starts with a C, C for combine. It means that you take the cosine of alpha and the cosine of beta and combine them. And you take the sine alpha and sine beta and combine them. And then you just have to remember that it's a negative sign there, rather than a plus sign, like in sine formula. I feel like I'm saying sine and cosine all over the place. Okay, so with just this, we can start to answer some more sophisticated trig questions, like the ones that I have as the examples, and I believe the ones that you have as your homework for this week. So, find sine of pi over 12 and cosine of pi over 12. So we know some values, right? We know what pi over 3 is, like the sine and cosine. We know what the sine and cosine of pi over 4 is. We know various things, but we don't know anything over 12. The way to do this is we notice pi over 12 is equal to pi over 3 minus pi over 4. And so I say we notice, but I didn't notice that the first time. I didn't think of that. The way this works is when you do the cross multiplication to get a common denominator, this becomes 4 pi over 12 minus 3 pi over 12, because this takes on a 3, this takes on a 4, and then when you take the difference, it is exactly pi over 12. So it's true, but whether or not you would observe that on your own is dubious. Anyway, now to find the sine of pi over 12, we know that sine of pi over 12 is going to equal the sine of pi over 3 minus pi over 4. And now we can use our angle sum formula. This is going to be the same as sine of pi over 3 times the cosine of negative pi over 4 plus the sine of negative pi over 4 times the cosine of pi over 3. Just plugging it into the formula we just had up. Now sine of pi over 3, this is root 3 over 2. Cosine of negative pi over 4, well, cosine of positive pi over 4 is square root of 2 over 2. And when we do it over here, the cosine, it just becomes negative pi over 4 is down here. That's what was tripping me up, because cosine is an even function, which means it does not care about sine. So we can basically ignore the negative sign because cosine is an even function. And then cosine of pi over 4 is root 2 over 2. Then we come over here. Sine is not an even function, so it does care about that negative sign, but the way it cares is by factoring it out. So we can essentially just turn that into a minus sign, because the negative pi over 4 in here comes out into a negative 1 times the whole thing. So we get that this is now subtraction, and the sine of pi over 4 is root 2 over 2, and the cosine of pi over 3 is 1/2. So now we just have to combine everything together. One thing you could do is factor out a root 2 over 2 from the whole thing, and then you get root 3 minus 1 all over 2. Or you can multiply these together, at which point you would get root 6 minus root 2 all over, this should not be, yeah, that should be a 2, but then this should be a 4. Right, because 2 times 2. So, I mean, that's the way you find sine of pi over 12, is it's going to be either of these. And I got 2 battery signal things left, so I'll just quickly go through the next one, and then after this is essentially just more of the same, and then an introduction of the remaining trig identities, but I don't have any examples for those, so I think I'm just going to end it after I do cosine here. So this one turned into root 6 minus root 2 all over 4, and cosine of pi over 2, well, this is going to be the same thing. It's going to be cosine of pi over 12 equals cosine of pi over 3 minus pi over 4. And now we use the cosine angle sum formula to give us, this is the cosine of pi over 3 times the cosine of pi over 4 minus the sine of pi over 3 times sine of, minus pi over 4. Okay, now, again, we still know all of these values. Cosine is still an even function, so we don't have to worry about that negative sign. And sine is an odd function, so this negative sign we can factor out into a -1, but then minus minus becomes plus. So now we have cosine of pi over 3, which is 1/2, cosine of pi over 4, which is root 2 over 2, plus sine of pi over 3, which is root 3 over 2, and sine of pi over 4, which is root 2 over 2. So we get nearly the exact same thing as with sine, but obviously with a little switcheroo. So we get, you could either factor out a root 2 over 2 here, in which case we would get 1/2 plus root 3 over 2, which is going to be 1 plus root 3 all over 2, or we can do these multiplications and then add them together, at which point we're going to get that this is root 2 plus root 6 all over 4. And so that's how you would go about finding these things. The next example in here that I don't have enough time to cover right now, but which is in the notes, is for the sine of 7 pi over 12. And for that one, the thing you have to notice is that 7 pi is the same as, so 7 pi over 12 is the same as pi over 3 plus pi over 4 instead of minus. Because again, this is going to become 4 pi over 12, and this is going to become 3 pi over 12, and 4 pi plus 3 pi is 7 pi. There's nothing else in math that's quite the tongue twister as trig. But okay, so that is all of sections 4.5, 4.6, and 4.7. The remaining notes I am desperately going to try to get out this Thursday, so 2 days from today, because that's going to be the end of chapter 4 and the end of the material that's going to be on the final. Again, the final is going to be on May 7th. It is going to be covering all of chapter 4, and it is going to be on WebAssign. I'm going to do the exact same thing. In fact, tonight I'm going to email out the academic honesty statement that, yes, unfortunately, you will have to write out again. So please do not use the same picture that you used for the midterm. But yeah, that's it.